Hello, fellow. My name is James Owusu-Appiah, and I believe in innovation and doing things differently. This video has been prepared for you to guide you through some well-known concepts that will aid your studies and preparations towards exam. Due to COVID, we cannot meet in person to discuss, so I hope this video finds you well and helps you achieve excellence. Thank you.
And then locate the signal for clear, and so this is the micro instruction counter the clear signal. So we'll set the signal high. Now let me show you something that I would like for you to see on a clear. So what do you see this clear, right? Let me get this thing back. See the clear, right? This is clear, and let's see. Say clear when 1. So we set to 0 asynchronously. So take note of that word asynchronously, right? So which means it does not wait for the clock. This is an asynchronous signal. It doesn't wait for the clock. So keep it in mind. It does not wait for the clock. So keep that in mind. I will come back there. So let me just comment it. So clear micro instruction counter. So the micro instruction counter. So we are just clearing it at this particular step. That's what we are doing. To generate all the instructions needed for the jump. Now we just have to kind of compile this and then generate the final circuit from this table, from this truth table, so that we can have a circuit that we can insert here, and then our control unit to be ready. So let's generate the control unit. Now basically we have like there are about 2 approaches that we can use in generating this control unit or in processing the truth table. So we could go through the manual process of doing the Boolean minimization, and then creating and then finally followed by generating our logic circuit from the minimized Boolean expression that we'll have. Then we generate our logic circuit. That is one approach. And another approach is that we can also use a room, right? So the room can actually replace any combinational logic. That is one thing. You can use a room to replace any combinational logic. So you see later on how that will be done, because the approach that we will use is actually this approach. We are going to use a room, right? And then we'll basically store. What we'll be doing is that we'll store our table, right? This truth table will be stored in a room. So in that case, these are our inputs. Now there will be the address to select that particular output, set of output that we're interested in, or that particular state. So this address, this pin will go to the address input of the room, and then the output from the room will go to these things here, to the control signals. So that's the approach that we are using. Okay. So now with the approach of with that approach, right, the major challenge is kind of getting this data into the room. So you could do that manually. So okay, first of all, let's insert our room. Let's insert our room in a schematic. Since we say we are using the room, let me clear these things. Let me remove them. Okay. So let's insert the room into our schematic. So let's take this is the room. So let me take one input and bring it here. And then let's see how we are going to kind of how we are going to do that, right? Now once you have inserted, there's one thing you need to note about, since we are using the room, right? We need to make sure that you see, we have to take a room such that the number of inputs here, the width of the number of input that we have here should be equal to the width of the address width of the room, right? Because it's the address input that will represent the input of our function, right? And the output of the room, the data output, right, this number here should correspond to the number of bits or the number of output that we have. You see how many output do we have? So if you count all these our output after the column, you see that we have our 13 outputs, right? So we'll use and so our number of inputs is also 10. So if you count these things, it's 10. If you count here, it was our original distance, but I didn't show you these changes, how the changes came about. So sorry for that. So yeah, this is our table here, and then this additional, so this is our original table that we had, but these things are things are added, to just make this table compatible with Seacon, right? So I added this additional this thing. I added these additional descriptions here, just to make it compatible with Seacon. So basically, what this does is that, okay, it's so with using Seacon, we have to kind of like define all our inputs. All the inputs will be the inputs of our functions, right? Because all these are Boolean functions or something. The input of our table or something. So you have to define them and then get the state. And then one thing, Seacon is used for other purposes. So that's why it's not only for something like this, but it does it well. So that's it. And once you have done that, then this last line, what it this line tells Seacon that I mean, any other state that we didn't, any other state that we didn't, explicitly give a value for, just give it the default value of this. So it kind of help us to not waste a lot of time. And then yeah, so this is like a single statement. I won't talk much about Seacon, but you can follow the template. One thing I forgot to say was, I forgot to hint on was, okay, how are we going to do this connection? So let's first connect these inputs to our room, like connect the input to the address input of the room, and then connect the output to the address output of the room. So how do we do that? I'll use a wire splitter here. I'll use a wire splitter, and you can just look at the changes I'm making. So I'll be using a wire splitter. Let me just copy and then modify this one I have here. So basically, I want it to have about 13. I found out 10. Okay, this one. Let me rather copy this one on this side. So I'll copy and make the changes. Gotta make those changes here. Now, so I wanted to have a bit width of 30, because you see it's 10 input, so we need 10 bit for that. So 10 input, that is a bit width, and then I found out, so I also want it to be 10. I also want it to be 10 so that you can kind of follow. Okay, that was a mistake. I'm coming. Okay, let me do that again. So I'll copy something here, and then adjust the number of the bit width to adjust the bit width to 10, and the font out should also be 10, because we are going to use it for our address is our 10-bit address. And so let me make the changes. It's now 10. Okay, yeah, there's no need. So once this is done, now you have to take note of one thing here. You see, take note of something here. If you look at our bits here, how they are like, let's see from our table. You see these bits here, they are at higher order, so these are our higher order bits. So our lowest order bit for the input side is FBR0. So from here, our bits order are increasing. So keep note of that. Make sure that if you are doing this wire splitter, take note of it. Make sure you should do it such that the ordering should match here, because see, it starts from 0, 1, 2, 3. So these are the lower order bit up to the most, up to the higher order bit. It's increasing that way. So the 0 is the lowest, then the 8 will be the highest bit in this form. So we should make sure that it should matches what we have here. But in this case, see, this is our lowest order bit, FBR0, right? And this is our highest order bit, CIR3, this bit from here. So we have to kind of change the ordering of this wire splitter to match what we have here. So we can just flip it around. So this is what I'm going to do. Let me just copy this one here. I'll also do the same thing and adjust the bit width again. So here I need about 13 output, so let me set my bit width to 13. Okay, bit width to 13. Alright, then let me make my fan out to also be 13 too. So it's just the number of output that you have where you set it. It could be any number. I mean, later you can make changes and then you do those things. Let me so the same thing again. I want to make sure that the bit, so the bit ordering ready is very important here. So you see, this is the lowest order bit, but if you see from our output here, if you take note from our output, this bit right here, right, it's actually our highest, like the higher order bit that we have here. If we trace this bit by bit 0, this is a 0. So DMAR underscore IE. So if we check here, DMAR. So this is our highest order bit, and then this here will be the last. Here will be our lowest order bits here, the MICCLR. So if you see here, we need to make sure the ordering also matches too, as you can see. So our bit ordering are increasing in this way. So let's kind of match that.